Hi everyone, my name is Yewon and I'll be presenting motion planning of multiple unmanned aerial vehicles using deep reinforcement learning. So my research focuses on autonomous drones, otherwise known as unmanned aerial vehicles or UAVs. So why multiple UAVs? Multiple UAVs are used a lot in drone shows, search and rescue missions, and natural resource monitoring. And specifically, motion planning algorithms enable each UAV to find a trajectory from position A to position B, while also satisfying constraints, including UAV's maximum velocity and minimum separation distance. My research focuses on reinforcement learning-based motion planning algorithms, which have several advantages because it mitigates expensive real-time computations by encoding a policy function during an offline training procedure. And also, RL-based approaches don't require significant training datasets, unlike other learning-based algorithms. The specific algorithm that my project looks at is the DRL-FMP by Simnani et al. And this is essentially a hybrid motion planning algorithm of deep reinforcement learning, or DRL, and force-based motion planning, or FMP. How this works is essentially each drone determines the scenario's type. And if it determines that the scenario is a low-risk scenario, it goes with a DRL, deep reinforcement learning algorithm called the J3C CAT-RL NSL. And if it detects that it is a high-risk scenario about to collide with other agents, it switches to the FMP algorithm, which is more collision averse. There are several advantages of the DRL FMP algorithm. It has been shown to have superior performance to previous learning-based algorithms. It's collision-free and also scalable. However, DRL FMP has not yet been implemented on real UAVs, and rather it's only been tested on 3D MATLAB simulations. And this is a problem because MATLAB does not account for aerodynamic downwash effects that real UAVs experience. And what those are basically under the drones, we have these aerodynamic downwash that when a different agent comes under that UAV, it inhibits them from proceeding with their planned trajectory. So our contribution is that it addresses the gap that DRL FMP doesn't account for this aerodynamic downwash. And we did this by first studying past research on drone motion planning, which basically models UAVs as cylinders. And what this means is that in the algorithms, we pretend that these drones are cylinders, thereby forcing drones to be more vertically distanced.
And this is very sorry, Yewon. It's still on the first slide.
I thought it was a technical issue because everyone is frozen on, like, everyone's videos are frozen on my screen, but it looks like everyone's having trouble with seeing the rest of the slides.
Oh, okay. Do you see? Okay. Okay. What do you see right now?
That's the next slide. Oh, some other slide. Slide 11, it looks like.
Yeah.
Okay. Okay. Do you see my slides moving?
No.
11.
This might be because my internet isn't very strong, although I don't think it is. Okay, let me just try resharing. Okay. Can you see, what slide do you see right now?
14.
14.
Okay, that's really weird. So it doesn't seem to be letting me like move through my slides for whatever reason. Can you see it now? Like, what slide am I on?
12.
Now it's 13.
13?
Oh, I see
Okay.
12.
What
Yes.
about now?
Still 12.
I see
Now
10.
11.
Okay. Okay, I think it's just lagging.
Oh, okay.
Yeah. Can I just, I'm gonna try getting stronger internet by connecting to an Ethernet cable. Can I like represent in like a minute or so? Does that sound okay?
Sure.
I would say that's fine.
That's fine with
Okay.
me.
Okay.
Sounds good.
Sorry.
That's okay. It happens. We planned for these situations.
Not bad. Only one person had a major technical glitch, and I'm not even sure this is a major technical glitch, but this is amazing, this whole MS Teams platform. Are you guys excited to use it for your upcoming school year?
I think I am. I just wish students could make teams. I know that that's up to like the central U of T units.
Oh, right, students can't. Oh, but I guess Skype is built into the 365 platform, right?
Yes.
What's the dominant platform or video conferencing system that your courses are going to be using? Like, which ones are they using? Blackboard, I guess.
I
Yeah,
think
there's a built-in video platform for Blackboard.
Okay. You know, because I'm thinking about this going, it's kind of crazy if at the end of 4 years, let's say an entering first year student, if this goes on for a bit, you have the ability to become highly proficient in the use of a very sophisticated platform, Microsoft 365, right? But
Right.
instead, if they concentrate on Blackboard, you're learning kind of a useless platform because you're not going to use Blackboard when you go outside into the private sector or industry. But instead, you could actually kind of achieve a proficiency with this, which is, you know, the more I kind of dig into it, the more exciting it becomes about what's possible. Anyway, that's my opinion.
That's a good point. I hadn't thought about that. It's kind of like a house brand version of like a video conferencing software, Quarkus, BB Collaborate.
You have the ability, everybody does, to do kind of proficiency tests through Microsoft, right? So let's say, and I was just thinking about this the other day, if at the end of 4 years I become really good at moving between all of the apps and sort of demonstrating on one of their online tests that I can achieve 98 proficiency with 8 different apps within a single platform. You know, that's literally a skill I could put on my resume, I imagine, because if I'm going into an organization that uses Microsoft 365, you instantly become a high value asset because you can be a team leader knowing how to actually utilize the digital tools that you have.
That's true. That's very true. Adam Gerlach just said MS Teams has the most technical issues.
In terms of just malfunctioning, glitches?
I'm guessing. I mean,
Yeah.
today has gone pretty well, but
I think it's that in the back end, their video compression isn't too great, so it tends to be the most like laggy or like really suffers from poor internet connections.
okay.
All right, I'm ready. So, can I present?
Yes,
now?
go ahead.
Okay. All right. Sorry for the technical difficulties.
Yeah, no, that's not your fault.
Yeah. Okay. Oops. Okay. Oops. No, that's the wrong one. Let me Can you see the second slide?
I only see the first right now.
Oh.
I only see the first. Second.
Do you see the second?
I see the background.
Okay. Do you see the sixth slide?
Yes.
Okay. Yeah, I think it's just the internet lagging. Okay, can you see the first slide?
No.
I'm sorry, I think you should select the screen to present instead of the Microsoft presentation window. So that might help.
Okay. So
I think that's the first option that comes up.
Oh, desktop, like this?
Yeah, this should help. So if you click present now.
Okay. Do you see the first slide?
Yep.
Yeah.
And then now the second one?
Yep.
Yeah.
Yep.
Okay, yeah, that was the problem. Thank you so much.
Sounds good.
No problems.
Okay.
Thanks, Pranshu.
Thank you.
Okay. So I guess I'll get started. My name is Yewon, and I'll be presenting motion planning of multiple unmanned aerial vehicles using deep reinforcement learning. So my research concerns autonomous drones, otherwise known as unmanned aerial vehicles or UAVs. And we have the question of why multiple UAVs? Multiple UAVs are used in drone shows, search and rescue missions, and natural resource monitoring. And specifically, multi-agent motion planning algorithms help each UAV find a trajectory from position A to B, while also satisfying constraints, such as the UAV's maximum velocity and minimum separation distance. My research focuses specifically on reinforcement learning-based motion planning algorithms, which have several advantages, namely that it mitigates expensive real-time computations through encoding a policy function during an offline training procedure. RL approaches also don't require significant training data sets, unlike other learning-based algorithms. I'm studying DRL-FMP, which is a type of motion planning algorithm developed by Simnani AL. And basically, it's a hybrid algorithm of deep reinforcement learning and force-based motion planning, or FMP. And how it works is that it first determines the scenario type. And if it's a normal scenario, it goes with the reinforcement learning-based algorithm known as GA3C CAD-RL NSL. And if the UAV detects that it's close to nearby agents or otherwise in a high risk scenario, it goes with the FMP algorithm, which is more collision averse. There are several advantages of using DRL FMP, namely that it's been shown to have superior performance to previous RL-based FMP algorithms, and it's also collision-free and scalable. However, it has not yet been implemented on real UAVs, and rather previous work has focused on MATLAB 3D simulations. And these simulations don't account for aerodynamic downwash effects that real UAVs feel. And what these downwash effects are can be seen in figure 3. So essentially below each UAV, we have downwash velocity, and whenever a different agent gets close to the UAV, they oftentimes feel this velocity, and that interferes with their path planning. So our contribution addresses the gap, which is that DRL-FMP has not been implemented on real UAVs and therefore does not account for aerodynamic downwash. Upon doing literature review, there have been successful attempts at mitigating downwash effects by modeling UAVs as cylinders as you can see in figure 5. And essentially, this, by pretending that these UAVs are large cylinders, we can force these UAVs to be more vertically distanced and therefore mitigate downwash effects because the velocity it gets smaller as you go farther down below the UAV. So we focus on algorithm redevelopment by modeling the UAVs as cylinders in Simnani's DRL-FMP algorithm. And the purpose of our study specifically is to compare this new DRL-FMP algorithm against a control algorithm called optimal reciprocal collision avoidance, or ORCA. And because of the limitations to experimentation posed by COVID, we'll be using a physics-based simulation platform called Gazebo that basically simulates the aerodynamic effects. So our methodology first involves preparing the simulation platform. We're using an open source Gazebo model of Crazyflie, which you can see in figure 7. And this is a model of the actual Crazyflie, which is seen here. And we will integrate the DRL, FMP, and ORCA algorithms with the simulation platform. And then we will train the policy function through a multi-stage process and finally simulate both algorithms using 12 different test cases with an increasing number of UAVs, generate random initial and final positions for those UAVs to get to, and finally calculate the average percentage of successful scenarios, collision cases, and stuck scenarios. Progress has mainly focused on the preparation of the simulation platform. So far, we validated the Crazyflie 2.0 model, and also we are validating the control system. So the original control system that came with the Gazebo model is, it looks like this, and essentially it takes in the desired position and yaw of the drones, and also the actual position and yaw. And the reference generator takes those in along with the velocity to give the command roll pitch, thrust, and yaw rate. And this gets sent into the onboard controller, which also takes in several other variables to calculate the desired rotor angular velocities for each of the 4 rotors of the Crazyflie. And that finally gets sent into the Gazebo model. So far I've focused on the reference generator, which is shown here. And that one consists of several controllers, namely a PI controller for the determining the roll and pitch commands up here, and also a P controller for the yaw rate and a PID controller for the thrust command. We simulated the drone, a single drone from, and we made it go from position 000 to 111. And the graph here shows the results, and you can see that it never reaches the desired position, and it just fluctuates a lot. So we decided to redevelop the reference generator, and the changes that we made can be shown here. So instead of the 2 PI controllers for the roll and pitch commands, we decided to use a nonlinear controller. And finally, for the PID controller for the thrust command, we replaced that with a PD controller. And the result is that when we enter the desired position as x equals 1, y equals 1, and z equals 1, the x and y directions converge to the desired locations. But in the z direction, we still see some fluctuations, but it's still a significant improvement from what we had before. So the conclusion is that the original controller that we found is not robust enough yet for the algorithm simulation. So we've modified the controller and it now converges in the X and Y directions, but still oscillates in the Z direction. And for now, we're still inconclusive on the performance of DRL FMP in a 3D environment where aerodynamic effects are present. Our future steps are to fix the controller issue further, for example, by investigating the onboard controller, which we haven't yet touched on, and also simulate and test DRL FMP against ORCA. The implications of our study will be to inform the implementation of DRL FMP on real UAVs and further contribute to the development of reliable, collision-free, and computationally efficient algorithms for multi-UAV navigation. And that's it for my presentation. Thank you so much, and I'll take any questions.
All right, we'll go first again here for this presentation. I've got a couple questions related to the scaling of the cylinders. First of all, how big were the cylinders compared to the actual size of the quadcopter?
I don't know for sure because I haven't been involved in the algorithm development, but I think it was less than a meter.
Okay, but that would depend on the size of the quadcopter. So probably something, they looked like they were about 30 centimeters in diameter or something like that. So
yeah,
something on the order of 3 times the diameter as the cylinder.
Yeah. So
okay.
the
Okay,
crazy flies are pretty small. Yeah.
Right. All right. I suspect you won't be able to answer this question then, because it's about the effect of the downwash. Is it decreases in intensity as you get further away? And I'm just wondering if you kind of had if it made sense to have a flexible bottom to your cylinder, but I guess that's a little bit beyond the scope of what you were trying to do.
Yeah. Yeah.
Sorry.
So yeah, sure.
Another question. You did mention that you were actually planning to do dynamic flying tests with these devices. So do you have any plans to be able to do that going forward somehow?
Yeah, so this is actually a master's student's project, and I was planning on doing experiments with her, but given the situation where this simulation was supposed to sort of complement that in a sense, given that we don't have as many opportunities to work with real UAVs.
Okay.
Yeah.
So here's a question from outside the technical world. Can you update me? I know that a couple of years back, maybe more than a couple, there's a lot of talk of how drones are going to transform delivery. Amazon was the big example. It seems like a lot of media hype. What are the chief industries today that are employing drones, and are these the industries that your research has the potential to have the biggest impact upon?
Yeah, so the multi-UAV problem is probably the most useful for drone shows. So those are basically, I don't know if you've seen them before, but these days people are trying to, rather than use fireworks during ceremonies, they're trying to have like multiple small drones that have like light bulbs attached to them to have like to create images in the sky. And that's where this algorithm becomes really useful, because you're trying to get like these small UAVs from place A to place B, but also you want to avoid each other. So that's one use case. And another use case is when, say that you're going with the payload delivery and you want to have these drones move in an environment where there's a lot of pedestrians. In those cases, you would also want these drones to avoid the pedestrians. But given that this algorithm already accounts for like collisions with moving drones, it sort of can also be applied in a pedestrian-rich environment.
Okay, thank you.
Any other questions?
For judges, I put in the times for all the presenters in one spot. They were all under time limit. And that's all I have in terms of timekeeping and making sure everything was working smoothly in the back end.
All right, well, clap, clap in real world terms. You did a great job, all of you, and how exciting to be back getting ready for school again for me.
Yes.